This is my cellular automaton that operates in 2 dimensions to create a 3-dimensional structure. So one type of cellular automaton is 1 dimensional and creates a 2-dimensional display. And the way that happens is first you have a seed row. You apply a set of rules of and, or, exclusive or to each of the cells of that row. The information is then recorded in the next row. Those same rules are applied again for some number of n generations. My cellular automaton uses a matrix, applies similar rule sets. However, I've included some new rules that don't make much sense in 1 dimension. And so that will be count, even count, and odd count. To make sure that my cellular automaton is operating the way I expect, I've decided to do a 3-dimensional representation of Sierpinski's triangle. And you can see this done in the 1-dimensional aspect. Pretty common. And so here I'm going to apply my rules. This is applying the rules across one row, similar to the 1-dimensional cellular automaton. Like I mentioned, it's an exclusive OR, which is my rule set 3 here. So I'm going to get a 3-dimensional structure that parallels what you'd see with a 1-dimensional on a page, essentially. I've already created a seed matrix. This creates the very center cell to be alive. The colors are randomly generated, but you can start to see here, we start to get a separation as we would expect with our 1-dimensional. You can tell each slice essentially would be one row. So we're building up. Here's a rotation. You can really start to see the structure from a different point of view. As I mentioned, my cellular automaton can work in 2 dimensions. So we can take the same premise here, rerun our program, and apply the same rule set, but in 2 directions this time. To do that, I'm going to select a rule 5. So this would be essentially applying the exclusive OR in the X direction and the Y direction at the same time. 3 for exclusive OR. We'll use our same seed matrix. And now we can see that we get separation both in the X and Y direction at the same time, building this nice 3-dimensional structure. We get a nice rotation here once it completes, really being able to see what cells became alive and died during each generation. This is a very structured input, as you could imagine. So we can use something that seems more random and see what is built from that. Let's run our program again. This time we'll create a 100 by 100 matrix. Due to the size and complexity, we'll only go 5 generations. This time we'll go ahead and we'll look at all of the cells surrounding a given cell, and we only want a cell to be alive. Let's say if it's got even number of neighbors. Because I don't have a matrix that's 100 by 100, we'll go ahead and let the application build us a seed. So you can see here, obviously, lots of small cells. And each layer is essentially taking a look at each cell and asking, how many neighbors do I have? Do I have an even number of neighbors or an odd number of neighbors? Depending on the answer, the next row is storing the information. And we'll get a nice rotation in this last one to really see what this all comes together as. interesting enough, you can see there's a handful of cells that appear that they may never have been alive during those generations. Others, obviously, appear to be alive throughout. Uh, this looks very similar to a Minecraft map.